Who is this?
Huh? Who is this? I was just checking in previous year that system responds to handwriting. And
It's working.
so by now you do have vision how hard-to-talk theory works. And if your goal is to model materials and molecules, you need to predict values of observables that one gets on experiment, like activation energies, colors, ionization energies. And it is reasonable to focus a little bit on observables, at least some of them, and discuss how one is getting observables from the outcome of multi-alternative structure theory. We were covering this aspect tangentially a couple of times. So if we leave behind computational chemistry, focus on quantum theory, there is a bridge from world of wave function to the bridge of real world, to the observables. Sounds like someone is trying to. So it is procedure to find expectation values, right? So you take wave function Brian cat on the left and right, put operator corresponding to observable in the middle, and find expectation value. It doesn't surprise you, right? And one of the challenges is that when we were taking basic quantum theory or reviewing it, typically all these things are postulated for one electron function. Here it is multi-electron, weighted determinants or Hartree products. And it is interesting and practically important to see if this concept of expectation values is possible to implement the multi-electron wave functions, and which observables can be focused at in addition to total energy, which is a primary goal of most of electronic structure theories. So we will cover interaction of matter and light, just preliminary steps, which is needed for any spectroscopy, like UV, infrared, Raman, and so forth. And then we'll look at the Koopman's theorem at the end, and in between, I will throw in a little bit of information on solid matter and periodic systems, which is extremely important if you are hating small molecules and like practically big materials, and if you're doing whole graphene, there is a new material which sounds like same graphene, whole graphene, but it is whole of the word derivative of the word whole, graphene with cavities. So, but it is also periodic. And but when designing products for your final report, some of you will select something that is periodic. So I will throw in this idea. This will be not the most intellectual challenge. It's practically important, but quite easy. So you can do that. Understanding if you got the presentation that's typically when I move crazy to focus to what at least all class was very supportive of this idea. Everyone was applauding. And
you check the topic?
No, it is the same topic. This is what you originally, this is what you really wanted.
But my topic just was for some.
No, there were boxes. You are in the most preferred situation for the whole class. This subject was not covered yet, so it will be covered tomorrow, partially covered tomorrow in the lab. And this is likely you already have.
I will try to see how it works.
Okay. Did you watch YouTube presentations from previous years? Did you get this presentation? So if you need, you can watch it. You're not that alone. And this one will be primary subject for the first hour of the lecture. This one will be the second hour. Also, did you get the handout after I sent the lecture notes? I sent another video. So this complements today's lecture and also covers the concept of unit church. If you really want to express it in calculations, if you care only about practical aspect, there is a drop-down menu that draws all ions. These spheres covered from green to red based on whether it is positive or negative, and it writes how many electrons are there, or the number of the function, the partial charge transfer. The goal of any electronic structures theory, and specifically particle theory, is total energy. And as soon as we solve this iterative equation, as soon as we have molecular orbitals and Fock matrix, there is a way formally total energy is expected as it's found as expectation value of total energy operator between Bryan ket of antisymmetric scalar determinant. But there is it can be converted into the language of discrete matrix element between discrete orbitals, and it is summation of all occupied energies of all occupied orbitals. And number two is because right now we are doing closed shell, so each orbital has collapsed to that. Right? And this is very natural view. If we make our bow of cellular orbitals, we add energies of all occupied orbitals, we get but in addition, there is a summation, pairwise summation that takes into account matrix element of flow, repulsion, and exchange attraction. And if this term is added, then we get total energy of the molecular system. There is a thing that we will not use practically. It's only for very superficial and not. I don't think it is needed. But if you will look into the textbooks or in Wikipedia, and I hope that I plan to print a couple of pages from teaser pages from books. This is what is typically written in the text. So one is writing, and this is only, I'm not going to derive anything. It is only for information quantities. So when one is expressing orbital matrix elements, one is writing down Coulomb and exchange matrix elements between atomic orbitals. Right? So we need Coulomb and exchange between molecular, but molecular orbitals are different at each iteration. But Coulomb and exchange between atomic orbitals, they can be computed once and forever through this iterative step. And you do remember, or at twisting my dreams of that molecular orbitals are composed as superposition atomic orbitals with expansion coefficients, right? C, capital S indexes. If one takes this expansion coefficients, C star C, this way, this object is called density matrix, and then it helps to combine pairs of molecular orbitals on the basis of pairs of atomic orbitals. In the Hartford computational chemistry community, this notation B capital and indexes is some products of expansion coefficients, molecular orbitals or atomic orbitals. It is practically used for setting up the 1, 2, 3, 4, 5. 1, 2, 3, 4. 4, 5, 6. Okay, my share will be right up. We'll go one after another. And it is open book. If you have your notes, feel free to open them. So the goal is to get to the edge. Or if you're not sure, either volunteer to fill the first box. No? Okay. Then prepare. Whoever comes first has a chance which box to start.
What is the
Okay.
beginning?
So
What form? Which
this
equation will drive this?
we are trying to reproduce flow chart for Hartree-Fock theory. So, and if you remember anything, you can start either bring us a hint what it starts from, which could be like positions of ions into something else. You can go backwards and check what is in the diamond for this condition of convergence.
I can.
Yeah.
Condition.
Okay.
We'll set precision. Precision. There's return or equal to the.
Should you put delta E?
Yes.
Delta E total. And probably the sign should be in opposite. So delta E should be smaller than tolerance.
Yes, that should be more.
Yeah, you can just write over.
Right.
Yes. Excellent. Yeah. Thank you. Okay. Yes. I think you have a clear idea what to do. Just how to try. Coordinates and maybe tolerance limit. This epsilon. It is write whatever you like for it. Just R capital. If you start writing your words, you don't have enough space. R capital for positions. Maybe some I, because there are so many indices. And the comma epsilon because tolerance limit is zero.
Absolutely.
Yes, yes, the same as Roger.
Yes.
Good enough. Yeah, yeah. Thank you. Okay, 3 boxes, 3 people.
The second one.
So you try anything you like, but I'll start entertaining the audience, like warming up for that. In Hartree-Fock theory, we need initial molecular orbitals. We need to set up Fock metrics. We need to diagonalize Fock metrics to find energies in molecular orbitals. And there is a procedure of finding total energy out of molecular orbitals. So any of these steps can be added. Maybe the third one. I would put here. Or please write symbols like F equals something, because it is, yeah. Just keep OC equals 2. Equal and continue the equation. Let me look what you have in your circle. And it doesn't need to be exactly. The idea of Fock matrix is that it is one electron Hamiltonian. You can put it like this: small letter h, and then plus Coulomb minus exchange. So if you, supposing you have completed this course, you did nice projects, you presented on the World Symposium, your results are excellent, and then someone with the hand asks, how do you get the results? Which matrix did you diagonalize? I diagonalize Fock matrix. Doesn't include interaction with outputs. Sure, it adds Coulomb and flux exchange. So we need only this value. And what is inside? What is inside the brackets? You can put be creative. Just make a little arrow and write inside. And skip the indices. Just write the letter K for Coulomb and minus like J, and K for Coulomb in exchange. One with plus, another with minus. Oh, you're going to put a complete theory there. Okay. Okay, yeah, thank you. It's really impressive. And I was thinking that you could just Coulomb minus exchange. Something. Right? Okay. Yes. Okay. Can you please teach us something?
So you just have one block?
Well, we have two left, and I think that
What do you think of this one?
this is too complicated. This one is easier.
So here we should we have diagnosed Folk matrix also measure the
energy. But put the diagonalization of Folk matrix. Excellent. And should we, yes, vectors. Excellent. Super. Thank you.
So what's the question?
And
would like to measure the energy.
Just write the symbol E total and
minus, this should be minus Hamiltonian, right?
Huh?
This is the Hamiltonian.
Which one?
ES.
No, you in this index sub I, yes. Really.
So something here should be energy. Right?
Yes.
Yes.
Super. Let's applaud. Okay, and in this feedback loop, one is providing updated molecular orbitals or expansion coefficients into formulation of Folk matrix, because this symbol P, the symbol P includes the C coefficients. But in order to start this procedure, one needs to guess, make a random guess or some educated guess for C sub I coefficients. And just that symbol, C sub I. Is that it? Okay. Yeah. Yeah, good. Yeah, thank you. So I have forgotten. My original plan was to print this blank page, distribute, and make it as a little quiz, but you successfully completed it on the board. You skip the quiz and just assign additional credit to everyone who was here. So in some sense, now you are certified experts in hard-to-code theory. And with help of literature and computers and programs, you can be director of a project of how to write software for hard-to-code. It will be not instantly, but you have general idea, right? This is what was done in one of the previous years. So it's basically the same thing. And 4 years ago. And this is how we can update it with maybe a few more blocks and all details. So, in addition to total energies, there will be observables that we will consider right now. For start, one needs positions of lines and guess of molecular orbitals, and then one is going through putting these molecular orbitals into density matrix, use density matrix to formulate Folk orbital, Folk matrix, diagonalize Folk matrix to get the C coefficients and energies, and formulate the total energy. Then if total energy on the previous step and next step is smaller than requested tolerance limit, then one can report it as a success and avoid observables. Otherwise, I need to repeat. And by the analogy with optimization of geometry is that, in some sense, if you consider this projections of expansion coefficients as dimensions in our space, it is browse in the multidimensional space, finding a minimum. So the energy depends with multidimensional dependence of this C coefficient. So we browse in this space until we get deeper. Done with this aspect. Now, what is light? Or maybe who was exposed to any college physics? Electromagnetism. Huh?
In the airport.
Just in the curriculum, right? Right? Did you in high school. Electric field, charges, Coulomb attraction. Not a problem.
2 decades ago.
Have you seen this figure? Not a question, but the figure. Give me a little sense if you have no idea what it's showing. Do not hesitate. No one will see it. So you all have seen this figure, right?
Yeah, I see him.
Okay. I see that some of you are very confident. Some of you are like hesitant to say that you're not comfortable. In this static electricity and magnetism, there are like charges, magnetic dipoles or whatever, loops, coils with current, and there is like attraction, repulsion, etc. If we are going to dynamical aspect, for example, if we have a pulsing charge, if I have a sphere with a wire that communicates positive and negative, it will create changing charge, creates changing electric field, right? Changing current in magnetic coil creates changing magnetic. And there are Maxwell equations, which was the top of human knowledge level until the advent of quantum theory and Einstein discoveries, that changing electric field induces changing magnetic. Changing in magnetic field induces change in electric. And they are mutually compensating and transferring energy quickly between each other. I'm not sure if it is a good analogy of yin and yang in Oriental culture. Maybe it's not a good analogy. The simplest solution of Maxwell equations is what we see. Light or any radio transmission, any light that we see, infrared, UV that we do not see, is propagating oscillations of electric and magnetic field. The beam of light can exist even if we destroy the source, right? Because there is a speed of light. Or there is a little, I can have the laser pointer shine beam of light and then immediately burn and explode the laser pointer, but light will still exist, right? So it does exist independently of the source after it has been released. And in the simplest solution, light goes like with a front with a certain speed, and in this front there is a oscillations of electric strength of electric field. Right? Strength is what makes charges move, and strength of magnetic. They are always by the nature of these equations, they are orthogonal to each other, which is shown on this diagram. And these oscillations are periodic in both space and time. So if you suddenly freeze the world, absolutely freeze, and we have an opportunity to visualize electromagnetic wave, it will look this way. So in X and Y, it will be just the same. As we go along the axis, the electric field will go positive and negative with certain wavelengths. Magnetic field will also go positive and negative with certain wavelengths. And their wavelengths will be the same for electric and magnetic. The longer wavelengths, the more this wave is shifted to the red area or to the radio wave. The shorter, more shifted to UV or to X-ray or to gamma. Now, unfreeze. Then the stuff will move forward. So that if you now we allow time to propagate, but we look only on one point in space. And then in this point in space, electric field will oscillate, positive, negative, and magnetic field is positive, negative. So in order this is not electromagnetism, of course. Therefore, we only review the solution. If we want to represent this image as an equation, the good representation for electric field component only will be here. So the initial field position in time 0, and then we will also need to do a real part, but for all practical math, it is so much easier to use exponential instead of sine. If you were practicing signal processing and Fourier transform, you will become a fan of exponentials. And in this course, we also have. So exponential and then in the argument, there are both spatial part and time part. So if in this orientation, if we use this illustration, then instead of vector k, we will have only delta z in z direction. No, instead of r. Instead of k, then will be just projection k sub z. Generate 3 components, x, y, and z, kx, ky, and z. But if it is one-dimensional motion, I know the direction, it will be a scalar product possible projection of components. So 1 over k is wavelength. When it makes the full cycle, it comes to the same amplitude. At the same time, it depends on time. So omega is frequency, t is time. So when we make omega t equals to pi, the intensity of electric field makes the full cycle into it. So one can characterize radio waves either by wavelengths or frequency. They are mutually interchangeable, and their proportionality coefficient is speed of light. Have you seen 60 years old radio tuners, which are typically made of like a big wood box? No? Maybe. I probably should put here the image for the next year. In the old, right now we have a radio with digital screen telling which station you want to hear, but in the old-fashioned radios were different ranges, like short, ultra short, long waves, AM instead of FM. Ranges, one needs to turn the knob, and it shows how it changes from like 300 meters to 400 meters, and then you hear some noise until you catch the station. Right? So the labels are typically in lengths because you are tuning to a certain range. Now, why this subject is brought in here? It's not a electrical engineering. It's not electromagnetism, of course. You have an idea of why we need this in computational chemistry for characterizing materials and molecules. Please share your vision.
Because the molecule, they have the energy bandwidth, and they did the electromagnetic field according to their energy bandwidth. That's how we can catch the magnetic field.
Exactly. So the main properties of materials are characterized with instruments. Right? And there are instruments where you heat to melt their heat capacity, or when you squeeze and make the brittleness. But majority, more than half instruments are based on the concept of probing material with electromagnetic radiation. Like NMR is electromagnetic radiation of radio frequency. It interacts with nuclear magnetic moment. Raman and FTIR is infrared range. UAVs, it is like looking for a response. The X-ray diffraction is also interaction of electromagnetic radiation with matter. So it is of all ways to characterize material, the interaction of matter with electromagnetic radiation, or more narrowly with light, is most general approach to characterize materials. Therefore, we are bringing this component into it. So now, how does matter interact with this electromagnetic radiation? What happens to charge if we expose it to non-zero electric field? Position. It will get acceleration and start moving, right? What will happen if we change the direction of electric field? And after your charge started moving, we apply electric field in the opposite direction. Like I apply field to the charge, it starts moving. Then I apply field in a different direction. It stops and starts moving in opposite. Then I change field again. It stops and starts moving opposite. I apply field in the different direction. What will happen to the charge? Yes, the charge will start vibrating. Very good. And sometimes the molecules, not sometimes, often molecules and materials are neutral. Right? Total charge of molecules is zero. Number of positive and negative charges are the same. But even in the neutral systems, they can polarize. The positive and negative charges can be a little bit offset in space, which means molecule has a dipole. So what would happen to the dipole in electric field? If you have a dipole, like positive and negative charge on a certain distance from each other, and then we apply electric field, which is not parallel to the axis of the dipole. Yes, but on the very, very first instant of time, how would it move? If you look on a very short increment of time, like I bring a polar molecule, I apply electric field, and look on this molecule, what will it decide to do? No. In average, in net, it is neutral. So it will not move anywhere. But positive charge wants to follow electric field, and negative charge wants to move in the opposite. So, and since the length between positive and negative is fixed in a dipole, they will rotate. Right? They will rotate to align with electric field. Good? I think it is not a big novelty.
Depends on the position.
Huh?
Whether it is rotate or vibrate.
If there is no release of energy, if there is no dissipation, it will start rotating, because by starting this rotation, it will accumulate kinetic energy, and
it will be polarized by circularly.
Circular light is too much. we look on the linear polarized.
Linearly, yes. And
But yes, there is a way to, and by this instant, I was asking only about static electric. In static electric field, it just rotate and align with electric field. But now, if you change, or if you start oscillating electric field, it will start aligning one way or another way, right? What is the energy of interaction between the electric field and the dipole? Let me please keep thinking about this aspect, and I will reformulate it. For any process, for any mechanism, one can reduce complicated things into one number, into energy. if two things are interacting, there is an energy associated with this interaction. So if we know mechanism of how things interact with each other, one can set up which energy corresponds to this interaction. Why it is cool? Because we consolidate multidimensional process in one moment. Why it is practically needed in this class and in any modeling? Because energy is what comes into Hamiltonian. If you know the energy associated to certain interaction, we can formulate it with equations, put in the Hamiltonian, and then redo calculations. Like which, everything is written on the board. I'm asking the question, but the answer is already there. So, what is the energy of interaction between dipole, which is a vector, going from positive to negative, and electric field, which is on the certain angle? Dipole moment and electric field are non-collinear. They are two vectors, right? If they become collinear, if dipole aligns with electric field, the energy becomes less. So depending on the angle, energy changes. When angle is 0, energy is minimal. When we increase the energy, increases. So minus scalar product of dipole times electric field. If they are collinear, energy is minimal. If they're non-collinear, it increases. It's what one needs to add into the Hamiltonian. Good? Now, what we were discussing right now deals with classical picture of science, where there are no quantum particles. If we bring back the fact that electrons are quantized wave in nature, that can adjust to any change of the circumstances around them, the picture will be a little bit different. Quickly changing electric field induces promotion of electron from one orbital to another. But the measure, the metric, the rate, how quickly it will transfer, depends on two factors. Whether frequency of electromagnetic radiation is in resonance with the transition energy, right? And second, whether we have a dipole connecting these two orbitals. Everything before this second was a review of common knowledge. Right now, there was something very challenging philosophically. So there is a static dipole that may slowly adjust to it. And there is a transition dipole, which doesn't have the analogy in the classical world. It is the matrix. There is no analogy, visual analogy. It is matrix element of the dipole interaction between states of electronic system. In this, we have computed electronic structure and state determinant of the molecule, and then we artificially constructed Slater determinant for a molecule which is in excited state. We can use them as a Bryan cat, as initial and final state, and put this matrix element of interaction between dipole and external electric field in this Bryan cat. If this matrix element will be 0, it means this molecule at this transition energy will not interact with light. If this dipole moment is big, it means this molecule is able to respond to the light. So in addition to resonant condition, molecule should have specific high frequency polarizability to be able to respond to external stimulus. Okay? And this is one of the very general, very major concepts that is used to characterize materials. So we are going to bring some ideas toward this direction, and this all will be used in the class, in the projects. And the last chapter, last month of the course, will be focused primarily on this aspect of information. So, dipole and electric field. What is dipole? Is charge, positive charge, negative charge, and distance between them. What if we have a molecule with many positive ions, many negative electrons? How do we formulate the dipole operator? We can say that it is elementary charge times position of all ions times charge number of the ion, which will be 1 for proton, 2 for helium, 3 for lithium, and so forth. Right? And then summation for number of electrons and position of all electrons. Minus sign because electrons have negative. Okay? So it will be saying positive and negative separated by a specific charge. Good. Now, the task is to formulate Slater determinant for ground excited states and play this operator between them, and then evaluate this matrix element and tell whether it is 0 or non-zero. Okay? And this, I know that you're mostly interested in practical sides, and this lecture materials and equations can be boring. But this little aspect, I certify it's much easier of what we did before, and it is of much bigger practical value. So what we do has immediate implications, and we will see. So, I'm repeating. The goal is to construct Slater multi-electron wave function in ground state, multi-electron function in the excited state, and put dipole interaction matrix element between them. Because we are limited in time, in patience, and in space on the board to write, I will abandon the Slater and use just what for it, and I will use only two orbitals, so 2 electrons. There will be an example of a molecule with 2 orbitals. In ground state, orbital 1 and orbital 2 are occupied. In excited state, we promote electron from orbital 2 to orbital 3. Okay? We will form Hartree product of the initial wave function, of the final wave function, and find expectation and find matrix element of the dipole operator, which was introduced before. So for the ground state, we have a product. Electron 1 in orbital 1, electron 2 in orbital 2. Okay? We abandon positive charges because upon integration they will be eliminated since wave functions do not explicitly depend on them. So for dipole moment operator, I will use R1 plus R2, so it is simplification of this dipole moment operator. So we have already 2 components: initial ground state wave function and operator. Now we do need excited state wave function, which will be second electron on the 3rd order. Okay? Yes?
Yeah, here we put the second electron on the second orbital.
We are neglecting the spin, and telling that one electron, one orbital. Otherwise, it would be, I'm just simplifying the picture. There is a way to introduce spin, but it will be much longer.
No, I'm saying in the previous picture you showed there are three states.
Yes. So in ground state, first and second orbitals are occupied. First orbital is occupied by first electron. Second orbital is occupied by second. Okay. In the excited state, first orbital is still occupied by first electron. Second orbital is not occupied, and third orbital is occupied by second electron. Okay.
But why the operator is R1 plus R2?
Well, minus R1 minus R2, because negative charge of electron. If you want to be meticulous, it should be minus sign.
I don't know, so how do you do it? Keep this, yeah.
Dipole element.
I got it.
Okay. So if we just, I have completed this exercise before.
I got it.
And by integrating over constant, it gives zero contribution. So if you just remove this, it will be just summation of first and second electron, and total number of electrons from 1 to number of electrons which equals 2. So we are practicing transition from ground to excited. Ground is first and second, excited is first and third. Dipole element is summation of positions. And this angular brackets is integration over position of first electron, integration over position of the second. So we are looking for the matrix element. Two integrations, ground state, excited state, operator. The rest will be technical details. Anyone has questions to this formulation? No? So in previous year, we were a little bit ahead of time, and there were volunteers to do the practice. But if we open the brackets, we will see that there will be two terms. Everything here are 1, everything there, plus everything here are 2, everything there. And we will use orthogonality relation, that product of orbitals integrated over a certain coordinate will be 0 if they do not coincide, 1 if they do coincide. Two terms. What can we tell about these terms? In here, we can identify immediately that integration over R2 will involve orbital 2 and orbital 3, right? And orbital 2 and orbital 3 are orthogonal. Therefore, this term will be completely disabled. It will be multiplied by a factor of 0. In the second term, for integration over variable R1, we have phi 1 of R1. So this integration will give 1, right? And then we need to perform integration only over R2. For R2, we have phi 2 and phi 3, and in this R2 variable in between. If you got this idea, you are on the threshold of big discovery. It's really important. It simplifies all calculations and all world of computational materials science, like by orders of magnitude. So we do have only this, and this, and the rest is removed. So instead of finding matrix element between multi-electronic wave functions, we reduce it to matrix element in terms of only one electron. So in this example, we use 2 electrons, but the same result will go for like 10, 100, 1,000 electrons. Instead of multi-electronic wave functions, we'll reduce it into one electron matrix element. So just second term, integration over R1 gives 1, and here we have phi2, R2, phi3. And we can call it orbital, I would call it matrix element of going from orbital 2 to orbital 3. What is the benefit of this? It means that in order to assess ability of a molecule to go from one orbital to another one, although the molecule consists of many electrons, you can take only initial orbital and final orbital, find expectation value of dipole or position operator between these two orbitals, and it will answer whether this molecule will absorb or emit light, whether this molecule will interact with electromagnetic radiation. So it answers basically all questions of characterizing properties of materials, response of a molecule to external stimulus. Okay. I will show these things in details, but we are over time. But I briefly cover. Anyone needs to leave immediately? Okay. I will skip details and just give an introduction to the subject that will bridge old chapter and new chapter, and we needed to do it before your presentations. So if there is a solid state, which means that the same pattern in polymers repeats, then positions of ions in the new periodic cell is equal as it was before plus the standard shift. If you have a polymer, it's repeating the reproduced. Huh?
That is constant.
That is constant, yes. And if one is trying to find the electronic structure, then in this periodic system, then by going from one unit cell to another one, the wave function will accumulate oscillating exponentially. And I need to repeat it when we meet next time. It taught us before. Now, one more thing. 2 homeworks ago, you answered what is Hopman theory. Let me repeat it. In heart of theory, total energy is summation of energies of all occupied orbitals plus Coulomb minus exchange. Suppose I am very lazy and I do not want to write this. And in order to justify my laziness, I will tell electrons interact so weakly that this is negligible, or Coulomb is approximately equal to exchange. It is not right. This will be a big approximation, but if you make life much simpler, because instead of double summation, one will run only one summation. So in this approximation, total energy of so many electrons filled into the molecule will be summation of all occupied orbitals. This was presented on the presentations number 2 by Christian Niels, and I borrowed his figure because he did it very carefully. So if we get energies of molecular orbitals, each molecular orbital has 2 electrons. And then there is a band gap that we used for today's test. Now, and there is a certain energy that corresponds to ionizing electron in photoelectric effect. By giving so much energy, electron will be completely removed from the molecule and fly to the vacuum or to surrounding. So the energy difference between energy of HOMO and this vacuum energy, which is typically zero in your calculations, is very close to ionization potential. Energy because it is energy needed to remove electron to vacuum energy. So this is energy of HOMO. This is LUMO, which is empty. If the molecule catches an electron from outside, from the vacuum, it will be attracted here, and this amount of energy that will be released after the molecule catches outside electron will be electron affinity. How much this molecule has affinity to catch external electrons. Those two numbers, ionization energy, potential, and electron affinity, is something that is measured in the electrochemistry, in analytical chemistry cells. And it also relates to photoelectric effect. Now, almost done. I appreciate your questions. Well, let me do the same figure as Christian Newes did a couple of years ago. So I will do two diagrams. One where number of electrons is equals constant number of electrons. Another will be anion, which means one electron more. This one will be cation, one electron less. We have so many orbitals, 2 electrons on each, HOMO, LUMO. If you go to anion, everything is filled, we bring one more electron. Cation, we remove one electron from there. Now, we can be very careful and meticulous by changing charge. By -1 because electron is negative, or number of electrons +1, or by changing charge by +1 because we remove an electron. So, formally, we can define ionization energy as energy of the model with 1 less electrons, and energy which is neutral, is n electrons. Electron affinity will be difference between system when it has 1 more electron and neutral. These definitions in red are correct, and they can be executed even in presence of Coulomb exchange terms. So you just add charge and multiplicity to your models in Gaussian, which you will cover in the lab tomorrow, and subtract total energies, with and without extra charge. It will be absolutely correct affinity and ionization. But if we really in rush, if you do not have time to rerun the calculation with different number of electrons, we neglect Coulomb exchange, and we write down that for neutral systems with n electrons, total energies E1, E2, blah blah blah, En minus 1, En, adding them together. With 1 electron less, it will be E1, E2, blah blah blah, En minus 1, and then 0. If we subtract these two things, everything here will cancel, and only answer will be E subtract, which will be ionization energy. If you have one more electron, we will write it E1, E2, E minus 1, En, and plus 1. If you subtract it with neutral, everything here will cancel, and only this number will be affinity. So this one, energy of orbital number n, is HOMO, right? Energy of highest orbital. This one is energy of lowest unaffected. So this neglection of Coulomb exchange contributions, energy of HOMO and energy of LUMO, gives observables affinity and ionization. And this is Janak theorem. Thank you for the questions. Looking forward to see you in the lab tomorrow. And I'm also encouraging and expecting for the PowerPoint of your presentations by Wednesday midnight, so that I can upload them and our meeting goes smoothly. Done? Have a nice day. I'll stay here to answer any questions. But
So we are using the Cookman theorem for HOMO and LUMO, but it's not, although it's not accurate.
it is not accurate.
Yeah.
It is not accurate. And there is a easy way to correct it. Just recompute total energy with additional electron or lack of electron. And this is not a big problem. But if we do huge system with like 10,000 electrons, each calculation is so heavy and expensive that we want to avoid it.
It gives us easily how to calculate the ionization energy and electron affinity.
Mm-hmm.
So it's
It gives a little compass, a little navigation.
Yeah.
We can assess the property of material before we do more complicated calculations. If you like screen many models and we need to find the one with biggest electron ionization, you can do single point calculations, select good candidate between systems, and then further investigate it with more details.
Actually, didn't, but I think I have to learn it more.
Okay.
And from the ionization energy, we can calculate the water function.
Yes,
as Einstein said.
Exactly. It is very much related.
Yeah. Thank you, Dr. See you for
I have a question about the presentation. I have selected the topic symmetry in G09 software. So if we do it using, we go to the calculus if I make a benzene ring and then